Hello dear students, welcome to this program. Today we are discussing an interesting topic which is inter and intramolecular forces. Before discussing inter and intramolecular forces in detail, let's first know its objectives. First one is types and characteristics of intermolecular forces. Second one is hydrogen bonding and its types. Third one is effect of inter and intramolecular forces on different physical properties of organic compounds. Now let's start with the first objective, types and characteristics of intermolecular forces. Intramolecular forces are relatively weak forces between molecules that hold the molecules together in the solid and liquid phases. These forces arise within a molecule. These forces are covalent bonds in a molecule. Intramolecular forces are much stronger than intermolecular forces. Intermolecular forces result from the attraction between molecules as a result of partial charges or the attraction between the ions and molecules. These forces are relatively weak since they involve smaller charges separated by greater distances. The attraction between molecules are not nearly as strong as intramolecular attractions that hold the compounds together. Types of intermolecular forces. There are different types of intermolecular forces. Some of them are as follows. First one is ion dipole. Second one is dipole-dipole. Third one is dipole-induced dipole. Fourth one is dispersion forces. Dipole forces are the forces that act between molecules. The electrostatic attraction between the positive end of one polar molecule and the negative end of the another is the dipole force. Dipole forces are generally weaker than hydrogen bonding. Both of these forces are due to dipole moments in a molecule. Now, ion-dipole interactions. An ion and a nearby polar molecule attract each other and generates ion-dipole forces. Ion-dipole interactions are an important force in a solution of ions. The strength of these forces are what make it possible for ionic substance to dissolve in polar solvents. Ion-dipole forces are important in solutions of ionic substance in polar solvents. For example, a salt in aqueous solvent. Second one, dipole-dipole interactions. From the orientation of polar molecule in electric field, when polar molecules lie near one another as in a liquid and solid, their partial charges act as tiny electric fields that orient them and give rise to dipole-dipole forces. The positive pole of one molecule attracts the negative pole of another. Now, dipole-induced dipole interactions. These occur when ionic charge of one molecule induces a temporary dipole moment on an adjacent non-polar molecule by polarizing the non-polar molecule's electron cloud. A dipole near a polarizable molecule induces a dipole in the neutral molecule, leading to an attractive interaction. The corresponding potential energy is referred as d-base energy. Now, dispersion forces. The default intermolecular force present in all molecules and atoms is the dispersion force, also called as London force. Dispersion force are caused by fluctuations in electron distribution within molecules or atoms. Since all atoms and molecules have electrons, they have dispersion forces. The electrons in an atom or a molecule may at any one instant be evenly distributed. Hydrogen bonding and its types. polar molecules containing hydrogen atoms bounded directly to fluorine, oxygen, nitrogen exhibit an additional intermolecular force called hydrogen bond. For example, HF, NH3 and water all undergo hydrogen bonding. The hydrogen bond is a sort of super dipole-dipole force. The large electronegative difference between hydrogen and these electronegative elements, as well as small size of these atoms which allow neighboring molecules to get very close to each other, gives rise to a strong attraction between the hydrogen in each of these molecules and the fluorine, oxygen or nitrogen as its neighbors. The attraction is called the hydrogen bond. Hydrogen bonds can be separated into two categories. Water is the only substance we routinely encounter as a solid, liquid and a gas. At low temperature, it is a solid in which the individual molecules are locked into a rigid structure. As we rise the temperature, the average kinetic energy of the molecule increases, which increase the rate at which these molecules move. There are three ways in which the water molecule move. First one is vibration, second one is rotation and the third one is translation. Water molecules vibrate when hydrogen bonds are stretched or bent. Rotation involves the motion of molecule around its center of gravity. Translation literally means to change from one place to another. It therefore describes the motion of molecules through space. Intermolecular hydrogen bonding. Intermolecular hydrogen bonds involve same type of donor and acceptor. Intermolecular forces are the forces between neighboring molecules, atoms or any other particles. These can be attractive or repulsive forces. Attractive intermolecular forces hold substance together and therefore these are important to make bulk material. All the molecules have intermolecular forces between them and some of these forces are weak and some are strong. Intermolecular forces affect many physical properties. The strength of the attraction between particles can greatly affect the properties of a substance or solution. Now, intramolecular hydrogen bonding. In intramolecular hydrogen bonding, the donor and the acceptor are in the same molecule. Intramolecular hydrogen bonds form 5, 6 or 7 membered rings where geometric restrictions make them relatively weak. Because of the geometrical constraints, intermolecular hydrogen bonds cannot form with the optical geometry compared to the intermolecular ones, creating the possibility that the donor of an intramolecular hydrogen bond can form an additional intermolecular hydrogen bond with an appropriate acceptor located on the another molecule. A special type of hydrogen bond will form under these conditions. This type of hydrogen bond involves 3 centers, 1 donor and 2 acceptors. There is another type of 3-centered hydrogen bond with 1 acceptor and 2 donors, which is common when the acceptor has 2 electron lone pairs. For example, in a molecule such as water, the oxygen can be the acceptor of 2 hydrogen donor on 2 other water molecules. The intra and intermolecular hydrogen bond discussed already has a single donor with 2 acceptors. This type of 3-centered hydrogen bond, which is also called bifurcated, plays important role in many chemical and biological systems. For example, chiral molecular recognition, proteins, RNA, DNA, and carbohydrates. Now coming to the last objective, effect of inter and intramolecular forces on different physical properties of organic compounds. First one is vapor pressure. The vapor pressure is the pressure of the vapor of a compound in equilibrium with its pure condensed phase, that is solid or liquid. Vapor pressure depends strongly on the temperature and vary widely with different compounds due to differences in molecule-molecule interactions. The normal boiling point of a liquid is defined as the temperature at which the vapor pressure of a liquid is 1 atmosphere. The vapor pressure of a substance is an intrinsic physical property that plays a crucial role in determining its distribution to and from gaseous environmental phases. The vapor pressure is also crucial for prediction of equilibrium, distribution coefficients to and from natural waters such as Henry's law constant Kh. Now melting point and boiling points. Boiling point is the temperature at which a liquid changes to gas. Boiling occurs when the vapor pressure of a liquid equals the atmospheric pressure. Stronger the intermolecular forces, higher the boiling point. Higher boiling point means more energy is required to boil the liquid. It is harder for molecules to break away from each other due to strong attractions. When a liquid is placed in a container open to the atmosphere and then heated, its vapor pressure increases. If enough heat is added to reach the temperature when the vapor pressure of the liquid equals to the pressure of the atmosphere, bubbles containing vapor form in the liquid and the liquid boils. The boiling point of the liquid is defined as the temperature at which the vapor pressure of the liquid is equal to the external pressure. The normal boiling point is the temperature when the vapor pressure of the liquid is equal to 1 atmosphere. Because boiling involves breaking of intermolecular forces, the boiling point of a liquid is related to the strengths of the intermolecular forces in the liquid. Now coming to the melting point, the temperature at which a solid melts is known as melting point of that substance. The melting point is the physical property of a solid and can be used to help to identify a substance. In practice, a solid usually melts over a range of temperatures rather than at one specific temperature. For this reason, it is more useful to speak of a melting point range. Although the term melting point is usually used, what is meant is melting point range. If the compound melts over a very narrow range, it can usually be assumed that the compound is relatively pure. Conversely, compounds that melt over a wide range are assumed to be relatively impure. Besides melting over a wide range, impure solids also melt at a temperature lower than that of a pure compound. Now coming to the surface tension. It is the attraction between surface molecules in a liquid. Attractive forces at the surface pull molecules inward, causing surface molecules to be held more tightly. This is why liquids form beads or drops when sprayed. Stronger the intermolecular forces, higher the surface tension. Surface tension of a water is high enough that bugs can walk on the water. Surface tension is the measure of a force required to break the surface of a liquid. The surface tension of water can be seen in where an insect rests on the skin that results from the high surface tension of water. Surface tension results from different intermolecular forces experienced by molecules at the surface of a liquid and those in the interior of the liquid. Molecules in the interior of a liquid experience intermolecular forces in all directions. Molecules on the surface, however, are attracted to molecules only to the sides and below. Thus, they experience a net inward force. This net inward force pulls surface molecule towards the interior, minimizing the surface area and causing droplets of liquid to form a spherical shape. Surface tension can be measured using the angle between a horizontal surface and the tangent to the surface where a liquid droplet meets the horizontal surface, called the contact angle. The greater the contact angle when a droplet of liquid sits on the horizontal surface, the stronger the surface tension of a liquid and the better it resists the force of gravity to attain the spherical shape. Contact angle depends not only on the liquid but also whether anything is dissolved in it and the material in the horizontal surface. Now, viscosity. It is the resistance of a liquid to flow. For example, honey flows slowly, it has a high viscosity. Gasoline flows rapidly, it has a low viscosity. Stronger the intermolecular forces, higher the viscosity. Viscosity is the measure of a liquid resistance to flow. We commonly think of viscosity as a measure of thickness of a liquid, where for example gasoline is a thin liquid and the motor oil is a thick liquid. Like surface tension, viscosity is not highly predictable based on other properties of a liquid such as boiling point, but it does depend on intermolecular force strength. In general, strong intermolecular forces result in high viscosity of a liquid. Another property that affects the viscosity of a liquid is molecular structure, particularly the length of molecules. Long flexible molecules tend to become entangled and resist moving past one another as a liquid flows. As a result, some liquids with strong intermolecular forces such as mercury have a low viscosity. The individual mercury atoms move past one another with little effort. Stearic acid, an organic fatty acid with a long molecular shape, has a much higher viscosity than mercury, even though the compound has weaker or molecular forces than mercury. It's all about this topic. Hope you understood it well. Thank you.